Alright, so now today let's look at integration using tan substitution. So now this is for those where you have an integral of the form. So we actually have a squared plus b squared x squared like that. So as you can see, a squared represents the constant. Then we have a constant b multiplying the variable, which is x squared. So if you have anything arranged in this order, so this will actually require tan substitution. Or so this is just one of the cases. You may also have an integral where we don't have the root necessarily, but we have it as 1 over a squared plus b squared x squared like that. So any of these two forms will actually require tan substitution. So now if you have this, what happens is you can factorize out a squared from this, and then we'll be left with 1 over 1 plus b squared over a squared x squared like that. And then this is, can see that a squared can the root of a squared can be equal to a, so you can pull that out of the root, so we'll be left with that. And so where the integrand contains a square root of a sum of squares, you can use the substitution b over a x is equal to tan theta. So now this is an example where we use tan substitution. So just pay attention to the arrangement. So there is a plus sign, and then there can be a root or not a root necessarily, but this is where we use tan substitution. So let's look at some examples, and this will allow us to have a better understanding. So in question number 1, we're being told to evaluate the integral of 1 over 4 plus x squared dx. Now this is a number that actually requires tan substitution because it's actually in the order that we've mentioned. So first of all, we can actually see that we can factorize out the 4. So we'll have a 4 into 1 plus x squared over 4. And then therefore, we know that 4 here represents a 2 squared, so we'll have x over 2, bracket that, and a squared outside. So now we can do tan substitution. So now from tan substitution, you can see that we'll have this x over 2 shall be equal to tan theta. So we can say that x is going to be equal to 2 tan theta if we make x the subject, and then therefore dx d theta, which is the derivative of that, shall be equal to 2 sec squared theta. Then let's make dx the subject and shall be equal to 2 sec squared theta d theta. Then if we solve for theta, we can actually see that from here, right here, that theta shall be equal to tan inverse of x over 2. Then therefore, when you substitute everything back right here, we can actually see that we'll have 1 over 4 into 1 plus tan squared theta times 2 sec squared theta d theta. And then therefore, we can actually see that this 4 and this 4 to reduce, and we'll be left with a half. So the half can be pulled out of the integral. And then we also know that 1 plus tan squared theta represents sec squared theta. So we'll have sec squared theta over sec squared theta, which is actually equal to 1. So we're going to have 1 d theta, which is equal to theta. So in integrate 1, we have theta. So we have a half into theta plus c. But remember, theta is tan inverse of x over 2. So we're going to have a half tan inverse of x over 2 plus c. And that's going to be our answer. Alright, so moving on to question number 2, we're being told to evaluate 1 over 1 plus 16x squared dx. So how do we do that? So can I already say this actually requires tan substitution. So you can say that 16 is the same as 4x. It's the same as 4 squared. So we have 4x, then bracket, then we square that bracket. So now by tan substitution, you can see that we can let 4x be equal to tan theta. Now this is already okay because we already have a 1 right here. So this can be used directly. So you can see that if we make x the subject, x shall be equal to a quarter tan theta. So if we differentiate that, we have dx d theta being equal to a quarter sec squared theta. Then we can say that dx shall be equal to a quarter sec squared theta d theta. So now if we solve for theta from right here, we can see that theta shall be equal to tan inverse of 4x. Then substitute everything back into this integral right here, and we'll have 1 over 1 plus tan squared theta times a quarter sec squared theta d theta. Now you can already see that we can actually pull out the a quarter value, and then we know that 1 plus tan squared theta is actually sec squared theta. So we have a quarter into sec squared theta over sec squared theta, which is the same as a quarter into 1. But remember that the integral of 1 is actually theta. So we have a quarter theta plus c. But remember that theta is tan inverse of 4x. So our answer shall be equal to a quarter tan inverse of 4x plus c. And that's going to be our final answer. Alright, so moving on to another question. This was a question from UNEB 2018, and this was question 14b. So being told to evaluate, so this is one that has limit, so this is a definite integral. So the upper limit is root 3 over 2 and the lower limit is 0. So we have 1 over 9 plus 4x squared dx. So what do we do here? So now this clearly requires tan substitution, as you can already see, because we have a plus and then we can already see the arrangement. So this is a square and this is actually also a square. So we can actually factorize out the 9 and we have 9 into 1 plus 4x squared over 9. But remember, 9 right here is actually the same as 3 squared. So you can say it will have 2 over 3, because also the 4 here is also 2 squared. So we have 2 over 3x bracket that squared, and then this 9 is going to be on the outside. Now you can see that by tan substitution, we're going to let this 2 over 3x be equal to tan theta. Then if we make x the subject, x shall be equal to 3 over 2 tan theta, of which dx theta shall be equal to 3 over 2 sec squared theta. So if we make dx the subject, dx shall be equal to 3 over 2 sec squared theta d theta. So if we solve for theta, theta shall be equal to tan inverse of 2 over 3, as you can already see from right there. And then therefore we have the integral of this into over 1 over 9 into 1 plus tan squared theta, as you can already see from right here, times 3 over 2 sec squared theta d theta. Then therefore we can actually see that this 3 and this reduce, and then here we will be left with the 3. So 3 times 2 is 6. So we have 1 over 6 being pulled out into sec squared theta over sec squared theta, which is actually 1. But the integral of that shall be equal to theta. But remember that we have limits in this case, so we have to consider that. But theta, remember, is tan inverse of 2 over 3x. So we actually have to first substitute and put theta in terms of x before we actually apply the limits. So we have 1 over 6 into tan inverse of 2 over 3x with those limits. So now when we plug in the limits, we'll have so we have the group where we actually have the limits, the upper limit 3 over 2, and then the group where we have the limits of 0, where we actually have the value of x. So now we can clearly see that from this and this, we can say the 2 cancels, and then we have root 3 over 3. So now we can actually see that root 3 over 3, now we can see that root 3 over 3 is actually the same as, because tan inverse of root 3 over 3 is 30 degrees, but 30 degrees can be represented in radians as pi over 6, because pi represents 180, so 180 divided by 6 is the same as 30 degrees. So pi over 6 is the best way of representing 30 degrees minus 0. So we have 1 over 6 outside. So it's going to be 1 over 6 times pi over 6, which is actually going to be equal to 0.087266, and that's going to be our answer. Now you can either have it this way or you can leave it as pi over 36, which is actually still correct. Alright, so moving on to another question. So we're being told to evaluate, so the integral of 2x cubed over 16 plus x to the power 8 dx. So now this is also a number that actually requires tan substitution. Now the difference here is you can see at x to the power 8, and then this we have 2x cubed at the top. But now this should not scare anyone, because this is actually still as easy as any other number. Now what you can already see that this x to the power 8 is just the same as x to the power 4, which is actually squared. So this is actually still going to use tan substitution. Then you can already see that this 16 is the same as 4 squared. So let's pull out the 16. So we have 16 into 1 plus, so we have x power 4 squared over 16. And then we know that 16 is the same as 4 squared. So now we can actually see that when we factorize, when we pull that out, we'll have x power 4 over 4 squared, as you can already see right there. And then by tan substitution, we're going to let x power 4 over 4 be equal to tan theta. So therefore, x power 4 shall be equal to 4 tan theta. And then if we differentiate this, the derivative will have 4x cubed dx being equal to 4 sec squared theta d theta. Now this is how it's actually going to work. So now we can say that dx shall be equal to 4 over 4x cubed sec squared theta d theta. Then you can say that this 4 and this 4 cancel, and we'll be left with 1 over x cubed sec squared theta d theta. And then now if we solve for theta from right here, we can actually see that theta shall be equal to tan inverse of x power 4 over 4. So put everything back right here, and we'll have 2x cubed over 16 into 1 plus tan squared theta times 1 over x cubed sec squared theta d theta. Now we no longer have to worry about this x cubed because we can already clearly see that will cancel out with this x cubed. So this is going to be easy to solve. So we'll be left with this. So we can already see that 2 over 16 is the same as 1 over 8. So we can factorize that out. So we have 1 over 8 being out of the integral. In 2, because we can already see that 1 plus tan squared theta is equal to sec squared theta. So we'll have sec squared theta over sec squared theta d theta. And then therefore we'll have 1 over 8 into the integral times the integral of 1. Now the integral of 1 is going to be equal to theta plus c. So 1 over 8 theta plus c. But remember, theta is tan inverse of x power 4 over 4. So now we'll have 1 over 8 tan inverse of x power 4 over 4 plus c. And that is our answer. Alright, so moving on to another example. So we're being told to evaluate the integral of 1 over, now you can already see that we actually have some values inside a bracket. So inside the bracket we have x squared plus 9, and then we are actually squaring that bracket. So it's the bracket that's squared. So what are we going to do in this case? So now we can already say this is what we have. Now from the inside we actually have to rearrange that into the form that actually requires tan substitution. So now we can see that x squared is appearing first, but now remember that it's better to have them rearranged separately. Now fortunately, if we put this value here as 9 plus x squared, it actually doesn't change the meaning, so it's actually the same thing, and then we are squaring that bracket as we have originally. Now we can actually say that we can factorize out the value of 9, but now because we actually have a square outside this bracket, so we can actually say that this 9 shall also be squared when we pull it out. So we'll have 9 squared into 1 plus x squared over 9, and then squared of that bracket. Now 9 squared is 81, so we have 81 into 1 plus, now you can say that 9 is the same as 3 squared, so we'll have x over 3, then we'll square this entire group. So this is what we end up having right here. Now by tan substitution, we can see that x over 3, which is the value right here, shall be equal to tan theta. So now x shall be equal to 3 tan theta if we make x a subject. Now when we differentiate that, we'll have dx theta being equal to 3 sec squared theta d theta. And then makes dx a subject, and we shall have 3 sec squared theta d theta. Then if we solve for theta from right here, we can actually see that theta shall be equal to tan inverse of x over 3. And then therefore if we substitute all these values back, dx, and then substitute the value where we put x over 3, we can say to have 1 over 81 into 1 plus tan squared theta, square that, times 3 sec squared theta d theta. Now this 3 and this can actually divide. Now 81 divided by 3 is actually 27, so we end up having 1 over 27 right here into, now you know that this sec squared theta here remains at the numerator, and then 1 plus tan squared theta is actually sec squared theta. Now because of this other squared, so we'll have sec squared theta over sec power 4 theta d theta. Then when we reduce these, we will actually have 1 over sec squared theta. But 1 over sec squared theta is the same as cos squared theta. So we have the integral of cos squared theta. Now we're going to use the knowledge of even powers. So from the knowledge of even powers of cos theta, we know that cos squared theta shall be equal to 1/2 times 1 plus cos 2 theta. So that's how we change it into double angles. So now then the integral becomes 1 over 27 into 1/2 into 1 plus cos 2 theta d theta. Now we can actually see that we can actually pull out this 1/2, so the 1/2 shall multiply this, and we'll have 1 over 54 into the integral of 1 plus cos 2 theta d theta. So we have this. So now when we integrate this, we have theta plus 1/2. So this, when you integrate cos 2 theta, we'll have 1/2 sin 2 theta, a positive sin 2 theta from a positive 1/2 sin 2 theta from right there, plus c. Now next we can actually multiply in the 1 over 54. So when you do that, we'll have 1 over 54 theta plus 1 over 108 sin 2 theta. Now we can't leave it this way. Now we're going to have to first simplify this and put this sin 2 theta in terms of x. Now remember that sin 2 theta is the same as 2 sin theta cos theta plus c. So this is what we have right there. But we know that this 2 and this shall reduce, and then we'll have 1 over 54 times sin theta cos theta. Now what we are left with next is to just simply find the value of sine theta and the value of cos theta. Now we know that we already know from this question that tan theta is equal to x over 3. Now remember, tan theta actually represents opposite over adjacent. So that means that now our opposite is x, and then the adjacent is equal to 3. So now from Pythagoras theorem, we can actually find the hypotenuse. So we'll have 3 squared plus x squared being equal to c squared. So c is representing the hypotenuse. So c squared shall be equal to 9 plus x squared, of which c is root of x squared plus 9. So now we know what the hypotenuse value is. So if we know the hypotenuse, it means that sine theta is equal to x. Because sine theta is actually opposite over hypotenuse, so we have it as x over root of x squared plus 9. And then cos theta, which is actually equal to adjacent over hypotenuse, shall be equal to 3 over x squared plus 9. So when you substitute all those back right here, this is what we end up having. Now we can already see that when we multiply this together, we'll have 3x, and then when we multiply this and this, we can actually see that we'll have so we will square them and the root will actually go, so we'll have 3x over x squared plus 9. But theta is equal to tan inverse of x over 3, so we'll have this. So now what happens is, where this theta will have tan inverse of x over 3. But now we can see that we have 1 over 54 in common for both, so we can pull that out 1 over 54. So I have 1 over 54 into tan inverse of x over 3 plus 3x over x squared plus 9, bracket that, plus c, and this is going to be our final answer. Now next, we're being told to evaluate this example right here. Now this is clearly here we're going to also need tan substitution, as I can already see from the arrangement, because there is a plus sign and then there is definitely no root. But then I can see that 25 is actually the same as the square of 5, and then we have x plus 3, that bracket is also squared. So now we can set, I can factorize out 25, so I have 25 into 1 plus bracket x plus 3 squared over 25. Now remember, 25 is the same as 5 squared, so I can actually also combine these powers and we'll have x plus 3 over 5 squared, as you can see right there. So now I can use tan substitution. So at tan substitution, I can see that x plus 3 over 5 shall be equal to tan theta. So x plus 3 is equal to 5 tan theta if I make x plus 3 a subject. So x shall be equal to 5 tan theta minus 3. Alright, so when I find the derivative of this, I'll have dx d theta being equal to 5 sec squared theta. So if I make dx the subject, dx shall be equal to 5 sec squared theta d theta. Now let's solve for theta. So you can actually see from right here that theta shall be equal to tan inverse of x plus 3 over 5. Alright, so therefore the integral becomes 1 over 25 into 1 plus tan squared theta times 5 sec squared theta d theta. Now I can see that this and this reduce, and I'll have a 1 over 5 remaining. So I can pull 1 over 5 out. Then I also know that 1 plus tan squared theta is actually sec squared theta. So I have sec squared theta over sec squared theta d theta. Now these actually combine and then they'll reduce to 1. So the integral of 1 is definitely theta. But remember, theta was tan inverse of x plus 3 over 5. So now our answer shall be 1 over 5 tan inverse of x plus 3 over 5 bracket plus c. And that's our answer. Alright, let's move on to another question. So in this question, now we actually have a root involved. Now, if someone does not see this clearly, they may not actually know that this is actually tan substitution. But clearly, if you look at this question, you can actually see that you cannot use substitution method directly as it is. So now, because integrating this cannot give us a value that will cancel out with the x cubed directly. So now this is actually, because we actually inside the root we actually have if we know that 4 is actually the square of 2, and then we have x squared right there. Now here we're going to actually, you have to use tan substitution also. So now how are we going to do that? So we're going to see that let's rearrange that. So rearrange that as 4 plus x squared. That obviously doesn't change the meaning at all. And then what I can set, I can pull out the 4 from here, so factorize it out, and I'll have 4 into 1 plus x squared over 4. So now I can also see that now the root of this 4 here is actually 2. So now 2 shall multiply this x cubed, and I have 2x cubed into 1 plus x squared over 4. But now I also know that 4 is actually 2 squared. So now that means I'll have 2x cubed into 1 plus bracket x over 2 squared. So we're going to square this group right there. Alright, so now by turn substitution, I can see that we can let this value here inside the bracket x over 2 shall be equal to 2 tan theta. So x is equal to 2 tan theta if we make x the subject. So now we differentiate that, I'll have dx theta being equal to 2 sec squared theta. So now dx being the subject, dx shall be equal to 2 sec squared theta d theta. Now if I solve for this theta value right here, I can see that theta is going to be equal to tan inverse of x over 2. So now therefore the integral becomes, so I'll have 2 x cubed into the root of, now I'll have 1 plus tan squared theta times 2 sec squared theta d theta. Now what we are left with as a problem is actually this x cubed value right here. So we're going to need to do something about that. But now from the knowledge of this, I can actually see that if x is equal to 2 tan theta, it means x cubed shall be equal to 2 tan theta, then we cube that. So x cubed shall be equal to 8 tan cubed theta. So that's what we're going to substitute right here. So where there is x cubed, we're going to put 8 tan cubed theta. So this is what we have now. But remember that 1 plus tan squared theta is actually sec squared theta. So now I'll have this. So now the integral of sec squared theta is actually sec theta. So I have tan 16 into the integral of tan cubed theta sec theta times 2 sec squared theta d theta. Now I can see that I can pull the 2 can be taken out, and the 2 times 16 is actually 32. Now sec squared theta times sec theta is actually sec cubed theta. So this is what I end up having now. Alright, so now that we have this, we'll actually have to solve this in actually a wise way. Now the good thing is inside sec there is actually a value that when you differentiate sec theta, it will actually give us a value that is more like sec theta tan theta, which will actually enable us to cancel out a value of tan theta. So now what happens is in that case we're going to actually have to change this tan cubed theta a little bit. So now tan cubed theta is the same as tan squared theta times tan theta. So that's clear. So now this tan theta here is actually going to be eliminated somewhere along the process. So now we're going to convert this tan squared theta into a value that actually has sec squared theta in it. So you know that tan squared theta is the same as sec squared theta minus 1. So that's actually clear. So now that we have this step here, we can actually use U substitution. And now that U substitution will give us a value that will easily cancel out with this tan theta value. So now we know du d theta shall be equal to, if we make U sec theta, we know du d theta shall be equal to sec theta tan theta. So you can actually see that this tan theta will later on cancel with this tan theta along the process. So now we can say that if we make d theta the subject, d theta shall be equal to du over sec theta tan theta. Now this is U substitution. So d theta shall be equal to that. So now when you substitute that back in, this is what we end up having. We have this times du over sec theta tan theta, which this tan theta shall cancel out with that, and then this and this shall reduce, and then what will we have? So I'll have 32 into the integral of u squared minus 1 times sec squared theta, because this is what I get after reducing this. But now we can already see that we know what sec squared theta shall represent. Alright, so we have this, and then what we're left with is sec squared theta. Now we also need to convert this sec squared theta in terms of u. But good enough is we can already see that u itself is sec theta, so that means sec squared theta is the same as u squared. So therefore we can actually substitute and put u squared within. Now u squared, multiply the values in brackets, and we'll have 32 into the integral of u power 4 minus u squared du. Now I can integrate that. So when I integrate u power 4, I'll have u power 5 over 5 minus, integrate this and I'll have u power 3 over 3. So now this is what I end up having. But remember that u is actually sec theta. So now I'm going to substitute this. So I have 32 into sec power 5 theta over 5 minus sec power 3 theta over 3 bracket plus c. But now I need to convert this into a simpler form. So now I'm going to convert them in terms of cos and sine, but now these ones shall be converted in terms of cos. So I know that sec 5 theta is the same as 1 over cos 5 theta, and then sec cubed theta is the same as 1 over cos cubed theta. But now we already have these values as denominators, so they will actually multiply that. So this is what we end up having. So now to have it in this format, we can actually now remember something. Now we know that tan theta is x over 2, so that means if we put this in a right angle triangle, we know that this represents opposite over adjacent, so now x shall be the opposite and then the adjacent shall be equal to 2, because from SOHCAHTOA, tan actually represents opposite over adjacent. So now we need to find that hypotenuse. So from Pythagoras theorem, we have 2 squared plus x squared being equal to c squared. So c squared shall be equal to 4 plus x squared. So when we find c shall be equal to root of x squared plus 4. So that means that cos theta is 2 over root of x squared plus 4. So now when we substitute that back in, this is what we end up having. So where we have cos theta, we're going to actually put that. So now we have this. Now remember they're all to the power 5, and then we have this, but remember that they're actually to the power 3. Alright, so now I'm going to plug in the powers. Now I can already see that 2 to the power 5 is actually 32, and then this is going to remain with the power 5. Then 2 to the power 5 here, to the power 3 here is actually 8, and then this is going to remain to the power 3. Now next I can actually multiply the 5 in. Now 5 times 32 is actually equal to 160, and then 3 times 8 is actually equal to 24. So I basically have 160 over this, and then I have 24 over that. But because we have 1 dividing by that, it means we're going to actually invert them, and then I'll have this value denominator going to the top over the 160 minus this value denominator going to the top over 24. So this is what I end up having. Then I can multiply the 32 in, and then I'll have 32 and 160 reduce, and I'll have this over 5 minus this over, now this and this also reduce, and I'll have 4 over 3 cubed plus c. Now what I can actually see next is now, because this is a root, so this is actually like having x squared to the power 4 to the power a half. So I can have 5 over 2, so x squared plus 4 bracket 5 over 2 minus 4 into x squared plus 4 to the power 3 over 2 plus c, and this is going to be our final answer. Alright, so question number 8, we're being told to evaluate the integral of x cubed over the root of 4x squared plus 9, and then all those actually in bracket, and then we cube that bracket dx. So how do we do this? You can already see that this clearly requires tan substitution. So now this is what I have. But now we know that because they're under a root, this is like having them to the power a half. So this can be the same as 4x cubed plus 9 bracket to the power 3 over 2. And then I can see that I can actually arrange them into this format. So now this doesn't change the meaning, because I'll have 9 plus 4x squared to the power 3 over 2. Now I can factorize out the 9, and then if I factorize out the 9, I'll have this it in this format. But then next, 9 to the power 3 over 2 shall be equal to 27. So I have x cubed over 27 into 1 plus 4x squared over 9 to the power 3 over 2. But remember, 9 is actually the same as 3 squared. So now I can have this in the, so I can simplify this, and I have this in bracket as 2x over 3, and then square these, because also this 4 also represents 2 squared. So this can actually be simplified in this format. So now that I have them in this format, I can now actually use tan substitution. So by tan substitution, I can say that 2x over 3, we shall let 2x over 3, this value inside the bracket here, to be equal to tan theta. Alright, so I can cross multiply, and I can actually say that we shall have 2x being equal to 3 tan theta. So now if I make x a subject, x shall be equal to 3 over 2 tan theta. So now that I have this, I can now differentiate. So this x d theta shall be equal to 3 over 2 sec squared theta d theta. So if I make dx a subject, dx shall be equal to 3 over 2 sec squared theta d theta. So if I solve for theta, I shall see that theta shall be equal to, because the original one here, I can actually solve theta shall be equal to tan inverse of 2x over 3 from the original, because we had let 2x over 3 to be equal to tan theta. So that means theta itself is tan inverse of 2x over 3. So now if I plug all those back into the original integral, I'll have x cubed over 27 into 1 plus tan squared theta, then all those to the power 3 over 2 times 3 over 2 sec squared theta d theta. Now how about this x cubed right here? We'll have to do something about it. But now, good enough, from here we can actually know what x cubed will represent. Now if x is equal to 3 over 2 tan theta, it means that x cubed is equal to this cubed. So I have 3 over 2 tan theta, and I'll cube that. So now this is going to be equal to 27 over 8 tan cubed theta. Alright, so when I plug in this value of x cubed, I'll have 27 over 8 tan cubed theta at the numerator. So now next, the easiest way to solve this is because there are very many constants, I can actually clearly see that what I'll have is 3 over 2 times 27 over 8, I'll get the answer as 81 over 16. Then get that answer, divide by this value here, divide by this 27, and then what I'll end up with is 3 over 16. Alright, so now I'll be left with this. So I have tan cubed theta sec squared theta over sec cubed theta. Now what I can actually see that these can actually reduce, and I'll be left with tan cubed theta over sec theta d theta. Now this can even be simplified further, and we can actually see that tan cubed theta actually represents sin cubed theta over cos cubed theta. That's going to divide that by sec theta d theta that we have right there. But remember that sec theta d theta is the same as 1 over cos theta. So now this is the same as when you change this into multiplication sign, I'll have it as sin cubed theta over cos cubed theta times cos theta over 1. I can say this and this reduce, and then I'll be left with sin cubed theta over cos squared theta d theta. Now I also know that this sin cubed theta can also be the same as sin squared theta times sin theta. So now this is what I end up having right here. So now I'm going to try to put everything in terms of cos squared theta. So that means sin squared theta is the same as 1 minus cos squared theta. So now everything is multiplying this sin theta on the outside. Now the reason I do that is because from this value of cos, I can actually get a value that will easily cancel out and eliminate this value of sin theta. So that means we are good to go. So now we can use u substitution. So we're going to let u to be equal to cos theta, and then du d theta shall be equal to negative sin theta. So that means the theta shall be equal to du over negative sin theta. So when you start plugging that back, so that means wherever there is cos, I'm going to put that a u, as you can see here. So I have 1 minus u squared over u squared. Now we were left with this sin theta value right here that I said will be cancelled. So this shall multiply du over negative sin theta. So this and this shall cancel, and then the negative remains, and then the negative shall be taken outside. So I have a negative 3 over 16 into 1 minus u squared over u squared. Now this is going to be easier to solve. So now we know that u squared is the same as, so I can take it to the top, it will become u to the power negative 2. Multiply that in the brackets and have u power negative 2 minus, now in negative 2, so when I multiply this and this, so their powers add, and then we shall have a u to the power 0, which is actually 1. So that's why I have u to the power negative 2 minus 1 du. Now when I integrate that, I'll actually have u to the power negative 1 over negative 1 minus u. And then we can actually see that this is what I have. So I can take this u to the power negative 1 down. So I have negative 1 over u minus u bracket and then plus c. Now I can already set, I can multiply this negative sign inside, and then all the negatives will go, and I'll have 1 over u plus u bracket that plus c. But remember that u is cos theta. So now what I'll have is 3 over 16 into 1 over cos theta plus cos theta, close that bracket, plus c. But remember that tan theta is 2x over 3. So what that means is from a right angle triangle, that means that the opposite is 2x and then the adjacent is 3. So now let's first find the hypotenuse so that actually know what cos theta shall represent. So the hypotenuse, we're going to find it from Pythagoras theorem. So from Pythagoras theorem, we'll have 3 squared plus bracket 2x squared being equal to c squared. So c squared shall be equal to 9 plus 4x squared. So c shall be equal to root of 9 plus 4x squared. So now that means that's going to be our hypotenuse. So therefore, cos theta shall be equal to 3 over root of 9 plus 4x squared. So this is what we end up having. So now we know what we can represent our cos theta as. So now let's plug that in, and then I can actually say that because this is 1 over cos theta, that means we're going to have this inverted. So I'll have 9 plus 4x squared over 3 plus, where there's this cos theta, I'm going to just plug in this value as it is. So this is what I end up having when I arrange it that way. Alright, so next I can find the LCM, and then the LCM I can see is going to be equal to 3 times 9 plus 4x squared. Now if I get this entire value here, divide by 3, I'll be left with the root of 9 plus 4x squared. So if I get the root of 9 plus 4x squared times this, I can actually see that it will be like this value squared. So now their brackets will cancel and I'll be left with 9 plus 4x squared. Then if I get this denominator here divided by this, I'll be left with 3. And 3 times 3 is 9. So I have the numerator as 9 plus 4x squared plus 9. But remember that 9 plus 9 is 18. So I have 4x squared plus 18 as at the numerator. So now when I multiply in 3 over 16, I will have at the numerator, I can already see that this 3 and this 3 shall cancel. Then I'll only be left with the denominator. So I have 4x squared plus 18 over 16 into root 9 plus 4x squared plus c, of which I can actually set, I can still factorize out a 2. So when I factorize out a 2 from the denominator, I'll have 2 into 2x squared plus 9. Now this and this reduce, and then I'll have 2x squared plus 9 over 8 into root of 9 plus 4x squared plus c. And this is our answer. Alright, so moving on to the next question. I'm being told to evaluate this question number 9. We're being told to evaluate 1 over x squared minus 2x plus 5. Alright, so when I look at this question, I can actually say that first of all, we need to complete squares at the denominator. So we're going to consider the denominator value, which is x squared minus 2x plus 5. Now in the former video, I had explained how completing squares works, so I'm not going to show it completely. But when you complete squares, this is what we end up having. So I'll have x squared minus 1 bracket, x minus 1 bracket squared plus 4. Which can be 4 plus bracket x minus 1 squared. So I encourage you to just check my former video and understand how completing squares works. So now I'll have the integral of 1 over 4 plus bracket x minus 1, then square that bracket dx. So now I'll have 1 over 4 into 1 plus x minus 1 squared over 4. Now remember that 4 is actually the same as 2 squared, so I'll have x minus 1 over 2, then square everything right there. And then this is what I have. So now we can say by tan substitution, we can let this value right here, x minus 1 over 2, be equal to tan theta. So that means x minus 1 shall be equal to 2 tan theta, then x shall be equal to 2 tan theta plus 1. Then when I differentiate that, we can say dx theta shall be equal to 2 sec squared theta d theta. So dx shall be equal to 2 sec squared theta d theta. So that means when we solve for theta, now we can clearly see that theta here is actually tan inverse of x minus 1 over 2. So what that means is now theta is tan inverse of x minus 1 over 2. So now when you put that back into the original integral, we'll have 1 over 4 into 1 plus tan squared theta times 2 sec squared theta d theta. Now this and this reduce, and I'll have a half. So a half can be pulled out. Then you know that 1 plus tan squared theta is actually sec squared theta. So I have sec squared theta over sec squared theta, which is 1. So I have into the integral of 1, which is actually theta. But remember, theta is equal to tan inverse of x minus 1 over 2. So therefore, our answer shall be equal to a half tan inverse of x minus 1 over 2 plus c. Alright, so next I'll be going to evaluate this 1 over 4x squared minus 8x plus 7 dx. Now let's consider the denominator, and you can already see that this also requires us to complete squares. So by completing squares, this is what we have. So we'll be left with 4 into x minus 1 squared plus 3, which can be rearranged as 3 plus 4 into x minus 1 squared. Then put that back in, and then I'll have 1 over 3 plus 4 into x minus 1 squared. Now this clearly requires tan substitution, as I can see from the arrangement. So now what next I can see is I can factorize out the 3. So I'll have 3 into 1 plus 4 into bracket x minus 1 squared over 3. Now from our knowledge of integrals, now I can know that 3 is the same as root of 3 squared. So root of 3 squared will actually give us 3. So that means this can be rearranged this way. And also I can also say that 4 is the same as 2 squared. So that means when I pull out a squared from each of these, I will be left with 2 into x minus 1 over root of 3. Then I can actually square them together, because if I put the squared back into each one, I'll actually be able to get this, what I originally have right there. So this is the correct way of pulling out the squared. So now what I can see is that by tan substitution, this value right here, so I'll have 2 into x minus 1 over root of 3 being equal to tan theta. So that means x minus 1 is equal to root of 3 over 2 tan theta. Now if I make x a subject, x shall be equal to root of 3 over 2 tan theta plus 1. Alright, so next dx theta, if I differentiate that, dx theta shall be equal to root of 3 over 2 sec squared theta. So if I make dx a subject, dx shall be equal to root of 3 over 2 sec squared theta d theta. This is what I have. Now solving for theta, now we can clearly remember that theta from here, we shall see that theta shall be equal to tan inverse of this value right there. So that means theta is tan inverse of 2 into x minus 1 over root of 3. So therefore our integral becomes 1 over 3 into 1 plus tan squared theta times root of 3 over 2 sec squared theta d theta. Now I can already clearly see that 1 plus tan squared theta is actually the same as sec squared theta. Now 3 times 2 is 6, so I'll have root of 3 over 6 being pulled out of the integral into sec squared theta over sec squared theta, which is 1. So I have root of 3 over 6 into the integral of 1, which is theta. But remember, theta is tan inverse of 2 into x minus 1 over root of 3. So that means we have root of 3 over 6 tan inverse of 2 into x minus 1 over root of 3 plus c, and that is our answer. So therefore, I have an exercise for you. So these are integrals that you can actually integrate using tan substitution. So I encourage you to try them out, and I believe that after you've done them, you compare your answers to what you can actually see on the right hand side, and once your answers are the same, you'll actually know that now you're actually getting the correct answers. So these are the first 10 questions, and as you can see, the answers are on the right hand side. So just compare your answers to what you have on the right hand side. And now the questions continue. So there's question 11, and then there's question number 12. So these ones also have answers on the right hand side of each one that you can actually compare with what you get. So try this out and get better at trigonometric substitution using the tangent. Thank you so much for watching. Thank you so much for watching this video. I hope the video really helped you. If you did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.